Okay, this is just showing off now. And that's the music. Okay, so introduction to my project. This project is about the landing of the Mars Phoenix on Mars. Well, that's for better. The Mars Phoenix spacecraft. So basically, we're going to be looking at the path the Mars Phoenix takes as it enters the atmosphere. So when it starts entering the atmosphere, what it does to slow down, and then it eventually reaches a specific speed and then lands. So we're just going to look at the entire path of that. So how does calculus relate to landing on Mars? Well, advanced physics relies heavily on calculus. So the relationship between displacement, which is the position of a particle, velocity, and acceleration. So we know that velocity is a function of position, and acceleration is a function of velocity. So they're just derivatives of one another, or integrals, whichever way you want to look at it. So basically, we're looking at how fast the thrusters should decelerate to accommodate the specific speed at which the craft should be going when it's about to hit the ground.
Mars has been pulling us in. We're now traveling at 12,700 miles an hour. 7 minutes before touchdown, we hit the Mars atmosphere, spend 4 minutes of the 7 minutes of terror you referred to going through that phase. We decelerate from, as I said, 12,700 miles an hour all the way down to 1,100 miles per hour. And when the parachute inflates, it puts a force of 10,000 pounds per square inch on that parachute. We'll spend 3 minutes on the parachute. As we're coming down, we're slowing down even more down to 120 miles per hour. You see the landing legs deployed. And when we detect we're approximately 1 kilometer off the surface, not the circus, the real fun begins. That's when we will separate from our back shell. And then we touch down at 5 miles an hour. So those last 30 seconds actually take us from 120 miles an hour to 5.
So I had to cut that video down considerably, but I included all the parts that had the relevant math. So basically, the information we're given. So this happens all within 7 minutes. So basically, just pay attention to the numbers. So the initial velocity of this is 12,700 miles an hour. And the final velocity when it's at 7 minutes is 5 miles an hour. So the first 4 minutes, the thrusters are turned on, and the velocity is slowed down from 12,700 miles an hour to 1,100 miles an hour. So around when the velocity reaches 1,100, the parachute is released for the next 3 minutes and 30 seconds to slow it down to 120 miles an hour. Then at approximately 1 kilometer above the surface, and that's at the same time, the parachute is detached, the thrusters navigate down to the surface, making the craft's final velocity 5 miles an hour. So if we were to look at this in a table, you can see these are all functions of each other. This is the integral of this, which is something we haven't really gone over yet, but I'll go over it later. So the acceleration is just the derivative of velocity. We know that already. So right now we're going to go from the information they gave us, which is assume velocity, v of t, is linear. So t is in hours. So if we had so if we wanted to check the time at 7 minutes, check the velocity at 7 minutes, and we had a function already, we'd have to divide 7 by 60. So we'd have to, well, it's a dimensional analysis, you don't learn that. So we're going through a basic slope-intercept function, which is y equals mx plus b. So if we just break this table up into a piecewise function, because in each of these ranges, a different thing happens. From here to here, the thrusters are turned on. Here to here, parachute is turned on. Here to here, parachute is released. So we call these ranges A, 0 from x to 4, B, 4 from 4 to 6, 6.5, C, 6.5 to 7. So first, we're going to find the slope. So this is going to be the calculations. You can't really see that right now. You can kind of see it, but we're just finding the slope by doing change in y over change in x, so delta y over delta x, which is something we all know. So change in y being the velocity. So 12,700 miles an hour over 1,100 miles an hour over 4 minus 0, which is 4 minutes, and then divide that by 60, which is 1/15 of an hour. So from there, we get negative 174,000 miles an hour squared. So that's how much the acceleration is between 0 and 4 minutes. So that's how much, well, deceleration, if you want to call it that. So that's how much the speed of the craft is actually decreasing over that time. So if we want to actually come up with a function, we go with y equals mx plus b. So we just take a point we know. We're already given a point, so 1,100. So we know the velocity of 1,100 is when it's at 4 minutes. So m, which is what we calculated over there, is negative 174,000 miles an hour squared. So that's just that times the time, which we went over, and then plus b. We want to find b because we don't know. That's an unknown right here. So if we just do this is just basic algebra here. We find out that b is actually equal to 12,700 miles an hour. Therefore, the velocity function for 0 to 4 is negative 174,000 miles an hour squared times x, which is hours, plus 12,700 miles an hour. Okay. Calculations continued. So here I really don't need to stress what we're doing again. It's the same basic thing. We're doing this one more time too. So just find the change in y, which is just the change in velocity over the change in time. Make sure it's in hours, which is why I'm dividing it by 60 minutes. And then this, so we find out the slope of 4 to 6.5 is negative 23,520 miles an hour squared. Okay, so we're moving on, and we find out the velocity function of this is between 4 and 6.5 is 266.8. Okay, so we're moving on again. We're doing the same basic thing. So change of velocity over change in time, which is negative 13,800 miles an hour squared. So we're going down here. We find out b from that. So these are our 3 velocity functions. So from 0 to 4, 4 to 6.5, and 6.5 to 7 minutes. So now what? What the hell is an integral? Okay, so an integral, this dealie right here, is an antiderivative. So for instance, if we have a function f of x is equal to x squared, the integral of f of x would be the antiderivative. So basically 1/3 x cubed plus c. Now the c appears because there can be a constant in there that we don't know about yet. So if we were to take the derivative of this would fall off. This would become x squared. So f of x equals x squared. That makes sense. So now we know acceleration is equal, the integral of acceleration is equal to the velocity function, and the integral of velocity is equal to, I call it s of x right now, which is the position of the craft. So right now we're going from what we know. We're kind of working backwards from the bottom here. So we're plugging in formulas we already have. So then we're finding the integral. So d is this constant that we may not know about. So we find the integral by just, if we go back, it's 1,615 minus 13,800 x. So integral is that. So anyways, so we find out that the position function is this line right here. So moving on, we continue that again. You see the same basic thing right here. Just the same math, except now we're just using that point right there that we already found out. Now, here's where it gets interesting, is because we don't have a point for when it's at 4 minutes, which is the next range we need to find out. So we have to plug it into that function and make an approximation for that so that we can use it in the next thing. And we use it in the next thing, so we're assuming the position is negative 24.79529 miles, and we plug that into the next. So at 4 minutes, this is equal to negative 24.79 miles, and you see the same basic thing. It's the same formula over and over again. It's just repeated. So here here, this is implying that the initial altitude that the craft comes on is about 484.79 miles above the surface of Mars. So right there, that's a little bit that's a little frivolous, so we don't really need to. So why is the first value off? If we go back, we look, we try and plug in 6.5 here, we should get 0.62, we get 0.52. That's because we're making approximations from limited information. We have about 5, maybe 6 points that we're given. So from that, we're expected to make accurate functions, accurate estimates from that. That's not realistic. So we're doing extensive number manipulation. So we're actually making a linear function, and then we're making an integral of that linear function, and we're plugging that in. So what we have right now, this is displacement functions of the different ranges, velocity, this is acceleration. Acceleration is a constant because we're assuming this is linear. That's how we approximate. So this is the acceleration graph. You can see it's pretty basic. This is the velocity graph. You can see endpoint there. It changes like that. And this is the position graph. So basically, as it goes, it gets closer to 0. And you can see each endpoint signifies a different range. So that would be when the parachute goes off. So why does the craft need to decelerate at 914 meters above the surface rather than 100 meters above the surface? Okay. So there's several factors that need to be taken into account. So basically, you don't really need to read this, but if you think of skydivers, they have to release the parachute just right, because if they release it too early, then they begin to gain more speed, and they'll end up hurting themselves because of how much gravity has actually taken place. And then if they release too late, then the parachute doesn't actually decrease the amount of decrease their velocity enough because they've gained too much speed. So in conclusion, this is a loose approximation. We're given about 6 pieces of information, and we're working with large numbers, tens of thousands of miles an hour. And we're doing a lot of manipulation, but this is a pretty basic understanding. I mean, this isn't going to be accurate enough for NASA to use. So calculus is required at every step in order to correctly make a safe landing for the Phoenix spacecraft because of what we've seen here, because velocity, displacement, and acceleration all relate to one another. And that is it.
Thank you. All right. Wow. Derek, Stephanie, doing okay. You guys, we'll get you a light, and you just stay inconspicuous, and you guys can be used.
All right. We did the service learning option for the final project. So we had to complete 10 hours of tutoring at the ABCD University High School on Tremont Street. And we're just first going to talk about the difficulties about the service learning. So I'll start. I think that the school took more tutors than they actually needed because it was really hard to find time to actually come in. Personally for me, for the first 4 weeks, I couldn't go in because my tutor or tutee either wasn't there, or she said someone would be there and then there wasn't, and it was just really hard to start with, just because I don't think there were enough people that actually need to be tutored for all of us to tutor, because I know there are people in other classes and not just the math one. So yeah.
Well, my experience was in the opposite of hers. In the beginning of a few weeks, I would go every week and I would get someone to tutor. But then when it comes to the end, every time I go, it's either they send me back because there isn't anyone for me to do that with, or that they say that they changed my time, but they never notifying me. So it's kind of hard to communicate with them.
My experience is kind of a mixture of both, because whenever I went in there, I apparently was not on time. I was always late or always early, and I showed up the same time every week, but I was always accepted in there. But whenever I did have a problem, if I was sick or something, I was not able to communicate with Tanya, the person who coordinated it, and it made it very difficult in order to try to make up hours and coordinate everything into one session and stuff. So.
All right, and just like what we enjoyed about it, putting like working with Tanya aside and having to like coordinate things, like it seemed the kids were actually appreciative of our help. Like they're kids that like want to get out of high school, they want to start their lives, and they appreciate the help you're trying to do to get them their degree. So every time I worked with a kid, they were always respectful and eager to learn, and I enjoyed working with them.
Mine's too, because like every time I finish like to a person, they will say thank you, and it like really showed that they appreciate that like help them in some way. Even though it might seem like it's a big way for us, but to them it's like a big help. And I think it's good that we actually just put what we learn to help others.
I really enjoyed seeing a couple of students in particular. I mean, probably about half the students I tutored, it just seemed like I did the work for them. I just gave them the formulas to plug and chug. But I can recall 3 students that really, I feel like, understood what I was talking about. I feel like I really got satisfaction from teaching them something, because by the end of my session with them, they were doing the problems by themselves and they didn't need my help anymore. So that was probably most rewarding for me.
I personally didn't tutor math at all. I did physics the entire time, so I didn't really apply anything I learned here necessarily, but just the fact of like helping someone else in physics is math related, just not calculus related. So yeah. All right, we're done.
Thank you, guys. Let's see, who would like to go next? Yeah, okay.
Let's turn on.
Yeah.
Did this. Oh, good. Oh, it's on.
What did you do to my system?
Turn it on. No, it's right there.
Okay.
Trying to send this to you. It's being very slow. Still sending. Maybe this is right here. Yeah, F down. It.
Oh, this should be on. There we go. Okay.
This has been still working for a while. What is this? It's 8 megabytes.
Hey, where are they? Oh. I put them all on my flash drive this morning. Where are they?
I can scroll down.
Maybe they're in calculus 1. No. Oh dear. Oh dear. That's not good.
Yeah. Just really beginning.
I downloaded these all this morning.
So you can get-
And they should have, I mean, I put them in the presentations directory. Oh.
Also, in the interest of time, I can just go and you search for it.
Okay, yeah, you go. Oh, here.
Yeah.
Unplug me here.
This is gonna be.
Well, nice thing is, if we're hooked up to the internet, I can pull them right out of my email. Oh.
This is long. Okay. If you need sound, it's right there. How about that?
hate technology. All right, let me turn your light off.
Colors are all weird, but that's fine.
Can you turn one of the light is?
On this. Let me see. Is that better? Is that better?
I think the one with the backlight's off is supposed to be one. Okay.
Okay, so I did a short presentation on some of the origins of modern calculus and the great controversy, which I'll tell you about. So just some preliminary stuff before I get into the meat. As far back as the 200s in BC, scholars like Archimedes were doing some very basic mathematic problems that led into calculus. One of these is exhaustion, which is just trying to find an area of a weirdly shaped, a weird shape using like rectangles or other polygons that you can measure the area of, and just doing smaller and smaller. So you do like do a rectangle first. Do a rectangle here, here, and as you add more and more, eventually it'll get arbitrarily small to the actual area, and that's called exhaustion. Archimedes also did some work on tangents, and he was the first one to find the tangent of a curve that's not a circle. He did it with a spiral and kind of polar graphs, if you remember that from pre-calc. All right, so calculus is agreed by most mathematicians and historians that calculus, as we know it today, originated around the turn of the 18th century, so about 1700. Newton and Leibniz were two contemporaries in the late 17th and early 18th centuries. And the thing about philosophers back then and scientists is that there weren't many, so they're all kind of this big gentleman's club, and actually some women, and they, got together and discussed their ideas, and everyone knew everyone. And both said that they independently invented calculus around the same time, which is the late 1600s. And followers of each started throwing mud eventually, and claimed that the other was stealing from the other, and so on. So a little background on Newton. He was what's called a polymath, which is just that he was into all sorts of different things, philosophy, theology. He was big into alchemy, mathematics. He was master of the mint in England in like 1713, 1714 or 15, and he got into politics a little bit about the time of when Queen Caroline and King George came to power during the Hanoverian succession. Alchemy and theology were really the most important things to him, but he's most remembered for Newton's laws in Principia Mathematica in 1687. All right. Leibniz was kind of remembered as the polymath of that time period because he dabbled in theology, metaphysics, and philosophy and economics. He dealt with the idea of the monad, which is kind of influential. He was part of the court of Electress Sophie, who was the mother of Princess Caroline and Queen Caroline of England. I wrote Britain, but that was a mistake. And he was the tutor to Princess Caroline. So when Princess Caroline came to England, actually what happened is that she brought her court with her, and she brought Leibniz with her, and Leibniz actually had to work with Newton because he was in England at the time, working for the current government. So basically, calculus can be expressed two ways. There's differentials, which is what we call it, and there's fluxes, which is basically the same thing, but it's different notation. Leibniz published his work on differentials in 1675, and actually L'Hopital was one of the first to write papers on it in like 1680. But Newton actually didn't publish anything on fluxions till 1693. But he claims he began work on fluxions as early as 1666, and some friends of his back that up, and he had a strong reputation, so people believed him. And everything would have been fine, they both basically believed that they invented it independently. Fazio was the first to sling mud, and he claimed that Leibniz copied Newton and saw some of Newton's papers or something, and stole the fundamental ideas when he published his paper. And then in 1704, there were these mathematical journals that had started cropping up, and there was a review of one of Newton's ideas that was published that implied that Newton had actually stolen the ideas from Leibniz, and everyone thought that Leibniz had written it, which he didn't, turns out, but it was a big deal. Newton started manipulating the argument. Personal attacks started flying back and forth. It was a huge controversy. That was in about 1714, and Leibniz died in 1716. So the last years of his life were not happy ones, because he pretty much lost the battle. Because Newton, was well respected, almost revered, and Leibniz lately did not have much repute. Newton and Leibniz actually didn't really disagree on calculus. What they did disagree on was a lot of theology, and a lot of things like their belief in free will. In the end, they grew to be miserable enemies. It was really the followers of each philosopher that were slinging the mud, and they all saw it as direct attacks toward them. So to each of them, it was the other guy being mean and them just trying to do math. And they were forced to work together for a short time under Queen Caroline, because Queen Caroline was a great uniter, like her mother, the Winter Queen, and Leibniz died in 1716. So, of course, the debate paused out of respect when Leibniz died. It eventually, kept going for a long time. There's convincing evidence today, when we look back at Leibniz's notebooks, that he came to develop calculus in a completely different way than Newton did. So the evidence supports that they just invented it at the same time without knowing that the other one was inventing it. Most historians and scholars now believe that both, Jesus did it on their own. Let's see. Are there any questions? Thank you.
Thank you, Tom. Okay, who's
Okay.
go? All right.
Did you get that?
Yeah, I do. Did you have a PowerPoint?
Yeah.
Oh, okay. It's not on here yet. I'm sorry.
Okay.
Somebody else should go. All right. Oh, yeah, that's pretty good.
It's not very long. It's really like that. But,
Oh, there it is.
on the next one.
I did a scrapbook on the mean value theorem. At the beginning, there's like some history and who proved the theorem, which was Augustine Lewis Cauchy. He proved it around 1821 because he wanted to teach his engineering students a new way to calculate limits and stuff. Then there's the proof, which all the mean value theorem says is that if you take the difference of endpoints and then it's equal to the derivative of a particular point multiplied by the difference of the endpoints, which just says that that there exists a point C between the intervals of A and B. And then it's basically that it's a tangent line, which is the point C, which is parallel to the secant line, which is the difference in the endpoints. And then there's just a couple examples.
You like to pass it around? Look at it. Okay, computer techs. Where are my
Hello.
computer techs? Please load this back up to the. That's right. Actually, while you do that, let's have one more person go before another computer one. So who's going to go now? Right? Excellent.
So my project was basically just doing crossword puzzle, like covering all the material that we did this semester. And yeah, I've heard one for everyone team. I have the one plus. It's like as to now among yourselves. Oh, and the last number on the very bottom, it's supposed to be pi divided by 4.
It's missing pi divided by 4 now. Okay. Chris, you want to? Sure. No, I think.
I can almost guarantee you top 40. Oh, interesting. Pie. Oh yeah. I bet this is gonna be something here. Screw
How do you,
it.
hey guys, how do you make it go?
F5.
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 F5. Up.
Click in it. That's all.
Yeah. There we go. Okay. Why is there a box there?
No, do the other way. You can see them. You can see the letters are put the other way. The lights.
Okay.
Yeah, that's
So we're creating
Ever,
that way?
Yeah.
kind of. Pull up.
Yes.
My 2 cents.
All right. Good morning, guys. So we spent a lot of time this year doing sines and cosines and stuff like that. And when we do cosine, sine, tangent, we're always talking about pi. And I was thinking to myself, like, I really don't know where pi comes from. I mean, we all know it's about 2.14, a little more, 2.14, 3.1415. I started thinking, my bad. So 3.1415, but there's more than that. So I was trying to figure out maybe where this came from, obviously, with like pi. So this isn't really the pi we're talking about, sadly. I'd love nothing more than talk about pi with you. But we're actually going to talk about the number and then the food. All right, so you have to ask yourself a few questions first. So what is pi? It's an irrational number, and there are no two numbers that you can divide, just real numbers that you can divide to get the actual number of pi. It's been calculated now by computers to about 10 to the 12th digits, like 1 trillion digits, and it just keeps going. It doesn't repeat. So there's a little song I found that some of you might have heard before. And if you haven't, it might... Alright, this is Pythagoras, yeah. So, if you've never heard this before...
it's muted.
It's muted. Alright, it's not on yet. Do you want to turn the volume on?
Well,
Oh, it's muted from there.
oh, I get you. Okay, now in principle.
That should work.
That seemed to fix it.
Oh, yeah. Can you guys hear that? I tried to find the phone number in here. I got 3 digits. I don't know if you guys know more. See if you can beat that. You can sing along and get bonus points.
I'm now out.
What?
I can't do it anymore.
No. I didn't do this, by the way. This is just some video on YouTube.
Well done, sir. Alright, didn't actually.
So, alright, we get the picture. It goes on for a little while.
Actually, we get the song.
This song, yeah. you can hear it's actually kind of a catchy beat too. So when I first heard the song, it was stuck in my head for a little while, which wasn't that good. Does it ever end? No, it doesn't ever end. Like I said, it's been calculated to over 1 trillion digits today, and computers going. We can never actually sit there and write it out faster than computers could calculate it. So I believe the trillion digit is 0. If you were wondering about that. All right, and where does it come from? So there's all these numbers you can see in these videos. People on YouTube just get these videos and they can make this about how many, I don't know how many digits were in that, at least 100. So where does it come from? So here are the ways you can get pi. All right, well first we'll start with ways you can't get pi. Some of you might have heard that you can divide 22 by 7 and get approximately pi. It's not true. Like I said, it can never be duplicated by dividing two real numbers because it's irrational. There's another one. Actually, if you divide 22 by 7, you get 3.142857143. So it's 3.14, but the rest is nothing. Also, if you divide 355 by 13, that's a different one. You get a little closer. It's 3.141592. That's not what we're looking for. So that's actually not how you get pi. This is how you get pi. So back when they were discovering math and what pi was,
We've stopped.
they were trying to figure out circumferences of circles and all that. And every time they would draw their circles, and this is back in the day, they had to measure everything out. So they measured everything out perfectly, and they kept finding this number 3.1415. And so they figured it was important, and they did a little more work. And they came up, if you were going to have, pi that well, they came up with this formula, circumference equals pi times diameter, which most of us know. So to get pi, if you treat pi as an integer rather than a constant, you get circumference over the diameter equals pi. So if you wanted to draw on your paper a circle that you knew the exact circumference of and you knew the exact diameter down to the infinite decimal place, you could divide those two and get pi. But we can't do that. So people have created formulas like this guy, Viet. There's actually that first E looks like this. I didn't really know how to do that on a computer. So if you're like writing this down and for future reference, that's the guy's name. He came up with, He came up with a formula that you can get an approximation of pi for, except it's infinite, so it's as close as you can get. You can always go one more place, and it looks something like this. 2 over pi equals square root of 2 over 2 plus square root of 2 plus square root of 2. So in the first radical over 2 plus square root of 2 plus square root of 2 plus square root of 2. Oh. And so on. You just keep going like that. So you would take this whole part of the equation here, and you would put it over 2, or 2 over it, and you would get pi. And as far as you go, the further you go up, the closer you get to it. So I did that a little bit. I did just that. I got 3.14, and the rest was not too close. So if you did it a few more times, you might get closer. But what I found out was the formula that they have today is the Bailey-Borwin-Plouffe formula, like Plouffe. They call it the BBP formula. And this is actually the way that the computers will figure out pi. And it's a series, which is this is what we learned this year. So it looks like this. So, you put this function into the computer, and the computer keeps calculating all these numbers. You get very, very close to pi. This is especially the higher you go up in k. And on my notebook here, I have up to k equals 4. And when you add k equals 0, I'm not going to do all the work because it's a lot of decimals and big numbers, and it's not fun. But when you add up k equals 0, and k equals 1, and k equals 2, all the way up to k equals 4, you get 3.141592645. And when you hit the pi button on your calculator, you get 3.14.
197.
Really? Okay, so
You'd be making it up, we wouldn't know.
so just going on up to k equals 4, you can see I have the decimals right to 1, 2, 3, 4, 5, 6, 7. 7 decimal places after 7 decimal places. So if you kept going with that, you could get very, very close to that video that you showed. And I really hope that whoever made that video didn't sit there and calculate that out. But all these decimal places aren't really necessary. If there's a trillion, I have over a trillion digits of pi. But if you use pi to the 11th decimal place after the decimal, you can calculate the circumference of the Earth to an exact value within a millimeter. So all these decimal places are really necessary. If you go out to 39 places, you can calculate the circumference or whatever you're looking for in a circle. You can calculate anything in the known universe that we know, as far as we can see, or as far as we know so far. You can calculate to within the exact value of an atom, atomic atom. So, I mean, all these trillion decimal places, it doesn't really matter. All you need is 39. And you can calculate anything within the size of an atom. So, if you guys want to go further than what I did, I can show you my work and you can keep going, but I don't think it's necessary because we can watch videos now. Alright, that's it.
Okay. Obey. Your turn. I'll take care of it.
Alright.
I know where I'm going now.
So much different than
So in this presentation, I was trying to apply the calculus to one of the nature, which is rainbows. So here's a brief description of the rainbow. We all know that they appear after a rain, or you can make it by taking a tube and making small raindrops of water and applying in a sunny day, so you'll get a rainbow, and the shape of the rainbow is different depending on the position of the sun in the sky, if it's rising or setting. So if the sun was setting, we'll see the rainbow as a semicircle with the center and the horizontal line. And we notice that there's an angle of elevation which is 42 according to the observer. And in this presentation, we will prove that why is this the angle is 42. So this is a different rainbow according to the different position of the sun in the sky. but at the same thing, it has an angle of elevation which is 42 degrees. And in some cases, we'll find that there's two rainbows at the same sky at the same time. Actually, I don't really know what are these circumstances, but the angle of elevation of the second rainbow will be 51 degrees. See, there are two rainbows, but the second one will be fainter than the first one. And here's in blue. You can notice the second one here. So here are some physics law that we will use to prove that the angle of elevation is 42. The first law is called the law of refraction, which states that when the array of light meets the surface of two different substances, it changes direction and it bends its way. And the other one, a principle called Fermat's principle, which states that the light usually, and I think always, takes the quickest path to from the source to the eyes of the observer. So here's the law is N1 sine theta 1 equals N2 sine theta 2, and N1 and N2 are two constants depending on are constants, and these constants are measured. You'll find a table of these constants depending on the place of if it's water, air, or any different substances. So what happens when light travels from one media to another? By applying the law of refraction, we notice that light bends its way and it takes another way through the second medium, and that's what happens from when light goes from air to water, as in the case of the rainbow, when the light from the sun goes into the raindrops, it bends its way. And there are two angles. The first one is the angle of incidence and the angle of refraction, measured from the line of the source to the vertical line. So why does the light take the quickest path? I think we can apply the optimization problems to see that the path, the quickest path, the path that the light takes is the quickest path from the source to the observer. By using the optimization, maybe we can try it. I didn't think about it. I just thought about it yesterday, so because we take optimization. So there is another law that we will use called the law of reflection, which states that the angle of incidence equals the angle of reflection when the light hits like a mirror or any small surface. I think we all already know that from previous knowledge. So as in the case of refraction, we could apply this principle that states that the light takes the quickest path from the source to the observer, and this path is shown the middle one. You can see it. We can take the rainbow and zoom in it, so we can apply the two previous laws in this case to see what happens when the light sun goes through the raindrop. this is what happened. The rain. This is the raindrop, and the light from the sun faces refraction when it goes from air to water, and then the same thing happen when it goes from the water, which is the raindrop, to the air, faces the refraction here. So there are two refractions in the case of the rain drop, and at the end, the wall of the raindrop, we notice that there is a reflection of the light, and actually sunlight will not take this path. Some of the light will pass through the raindrop angle. So by stating that the raindrop is perfectly spherical, we can notice the following. The light strikes the raindrop with an angle called the angle of incidence. Leave the water drop with an angle of incidence too. No, an angle of incidence applies to when the light strikes the raindrop and the light leaves the raindrop. And inside the raindrop, you could see that there's a reflection at the wall of the raindrop. So what is the turning angle? As you saw the previous slide, so we noticed that there is two triangles here. This is the angle of incidence and angle of refraction, angle of incidence, angle of refraction, and this is the turning angle, which is the angle of which is the measurement of the light that turns from once it comes to the raindrop and leaves the raindrop. It turns by this angle. So the total angle by which the rays turn is encountered with the raindrop measured clockwise from the left is called the turning angle. So we could see that when the light entered the raindrop and leave it, turned by an angle equal, alpha minus beta, which is, this is alpha, and this is beta. So we could say that this is alpha minus beta, which is this angle, and the same thing happens. But in this situation, the angle is, this is beta, and this is beta, so this is 2 beta, and this is 180. So this angle is 180 minus 2 beta, which is the turning angle of this in this situation, which is 180 plus 2 theta, plus 2 180 plus 2 alpha minus 4 beta. So why do we only see the turn lights from the band 24 degrees above the axis to the sun? This is what we are trying to prove. So we'll take the turning angle, we'll differentiate both sides with respect to alpha. We get 2, this is 0 and this is 2, minus 4 dB over d theta. So how do we so this is called function number 1. So how do we measure dB over alpha. So we'll use the law of refraction, which states that sine alpha equals k sine beta, and k is the constant depending on the. So by differentiating both sides, we get cosine alpha equals k cosine beta dB over d theta, and by plugging this function into the function number 1, we get this function dt over alpha equals 2 minus 4 cosine alpha over k cosine beta. So we could apply also the linear approximation to this function, and we'll get the top function. So when t equals, no, this is actually t prime. When t prime equals 0, we'll find that t alpha equals t alpha, which is the t alpha 0 and there should be the alpha minus alpha 0 should be small, so we could apply this function, and by using the function sine squared the angle plus sine squared angle, we could apply it using some calculation, and assuming that k equals 1, 2, 3, so alpha 0 is 594 degrees, so the turning angle is 138 degrees. So 180 minus 138 equals 42 degrees, which is the angle of elevation according to the observer.
Thank you. Okay, your turn. So anybody watching the clock knows we're quickly running out of time. If you have another class immediately after this, I understand that 15 after you have to discreetly get up and go. Otherwise, of course, I'm sure the people who are still going would appreciate it if we could try to get as many of these in as possible.
So for my presentation, I just to write a paper about the history of calculus, and I choose to visualize what I wrote in research. So in the front of the t-shirt, I've stamped the figures of the two founders of calculus, which are Newton and Leibniz, and on the back of it, I've stamped the fundamental theorem of calculus, stating that integrals and derivatives are inversible. And I've listed the three main topics that deals with calculus, which are limits, derivatives, and integrals. I'll pass around you guys a brief chronology of calculus and a graph that visualizes what calculus study and the main figures that helped in the development of calculus. So, I think that should be it. Thanks.
And move your paper now.
Make any more of them? No? Alright.
So that's about it.
So you say
Yes.
you should have taken it first.
If I
Okay, thank you. Let's see. Alan.
Okay. I read a book that's called A Romance of the Many Dimensions, and I had it at home, but it's in Chinese version, so I bet you guys cannot read it. So I was going to talk about a summary of this book, but it's gonna take too long, so I'll just talk about what I feel on this book. And at first, I thought this book is a math book talking about proofs, equations, history of math, and so on. And however, this book is more like a book of symbolism using math as a tool to make people picture the history and the era of certain time vividly. And I find it really interesting to symbolize the world with mathematics, even though this book is not really a math book. I feel I could understand what the author tried to say because of his fine use the mathematical knowledge. And in similar way, I can also symbolize the people with my February lessons from calculus class. And I think my work is F of excellent. People are some people are ostentatious and beautiful, such as 129x to the 5 plus 1 million, which numbers what they show the society graphing patterns is beautiful with a lot of curves and shapes. And some equations are just simple as such as e to x. However, when I meet people personally and I get to know them more and more, I can find their real personality. And my high expectation already get lower and throw away the accessory constant that has no big meaning but just embellishment. However, some people are simple and honest as they look, so they don't change such as e to x. And some people are two faces, they are only change. They can be nice sometimes, but they are really too. Such as sine x, cosine x, or ln to x. And I'm not sure what equation I am. So what kind of equation do you think you are compressing?
What equation am I? I'm a trig function. I like to think of myself as a piecewise defined function with a lot of vertical asymptotes.
There's one of those parabolic functions and stuff. What's it fun?
Well, I'm definitely concave about that. All right, thank you. Charlie. Just saying, you're next. Is there anybody else got some thoughts? Huh? Oh, on the USB? Okay, here. Just show your line. I said open. Thank you.
Yes.
You know, bonus DVD?
Did you mute your computer again?
I didn't intend to if it is. No, it's not muted. Should it be making music?
Nothing.
I did a project on fixing a roller coaster, although fixing and math is two different things. But calculus was invented to solve physics. You told me that. The brief history of roller coaster is the earliest roller coaster exists in the 1600s as the Russian ice slides. The structure was built out of lumber and a sheet of ice, inch thick covering surface. While you climb the stairs attached on the back of the slide, beat down the 50-degree drop and then just go down. It was the French who locked the cars by having the access slide down into a grove. Actually, it was ordered by the French, the princess of the queen or something, because she wanted to play the roller coaster even in the summer without ice. The first looping roller coaster was located in French.
When was
Don't know. America was first introduced roller coaster during 1800s. Okay, this is the brief. I wrote the brief thing about the roller coaster. Well, energy is conserved, but everything is not perfect in this real world. Energy could lose from different form. Energy could lose in heat from sound and friction else. Well, how does a roller coaster get its energy? First, it comes down a big hill, as you already rode a roller coaster before, and it has potential energy, which is mass times gravity times height. And as it goes down, it slowly changes to kinetic energy, a half of mv squared. Mass times velocity squared divided by 2. Higher the place first it reaches, the more energy it has stored to convert, so it can go through the whole loop. A smaller picture right there shows potential energy, gravitational energy, free fall, acceleration, yada kind of stuff. Also in the roller coaster, there has acceleration that's different from the other one. It's for the loop. That's called a centripetal acceleration. Yeah, and then times mass, something like that. I don't remember. Okay. For example of the roller coaster, it could be like a wave or like a loop. In this, I take form as a wave. So you can calculate that by A is the amplitude, sine times x over lambda times 2 pi. And then you can take the derivative of that. First derivative is of the a cosine times x over lambda times 2 pi. I hope I did it correctly. The first derivative is the slope.
Hold on 1 second. Did she take the derivative correctly?
I don't know.
I can't read that.
What's it
I don't
missing?
think so.
I guess it's
One divided by lambda, and also remember times 2 pi.
The
2
2 pi is a constant.
That's okay. So you have to use the chain rule. Yeah. Yeah. Okay. So you just there's a 2 pi over lambda that should be out front. But don't worry about it.
Oh, okay.
Okay. So there's some constant, extra constant that should be out.
The second derivative of the function is to find the acceleration. The third derivative of the function is to find the jerk. As you accelerate, as you're in the car, you can feel a jerk and then you just move forward. That's what you call the jerk. Okay. From the equation of F equal ma equal F equal mg cosine lambda minus bv, you can replace cosine lambda as a dot. What's it called? Dot product. As we know, norm A and norm B means the length of the A and B, and A dot B is going to be dot is a vector A and B. Well, some people may think you can kind of graph roller coaster in your calculator, use piecewise function. Yes, but not quite, because roller coaster is 3D. It can turn and go up. So maybe people can use cross product and some other thing to grab it. And that's it.
Okay, there's one more. Now would be the time if you have to go to another class.
What?
No, come on. The last one. You should go.
If I have to stand, you can do it. That effectively do nothing but make everybody.
I'm trying to get it done by either tonight or tomorrow morning.
And I'm not
I'm stupid.
Can I drop my paper off?
Just email it to me.
So we're saying Tuesday?
Tuesday, 1 o'clock. Yep. Fenton, 337. Not here.
Benson?
Fenton, 337. I'll email everybody.
Nothing on Monday?
Nothing on Monday. No, there's no,
No more review, no more.
that's it. You can come to the recitation tomorrow. Here, let's get you.
So I will finish it. I don't have to talk about.
Do what you know you need to do.
No, not. So today I'll talk about the effect of trigonometric properties in three-dimensional figures. This is properties of trigonometric functions, cosine and sine. As we know, the range is fixed from -1 to 1, and the domain is infinity to infinity. They change smoothly and inversely to the rate of change. The derivative of sine, as you know, is equal to cosine. And sine x is equal to cosine x, respect to x. And the cosine x over x is equal to new sine x, which is the reason why they oscillate. They are complementary to sine square x plus sine square x is equal to 1. And we see the graph, they are inversely and smoothly changing. This is the relationship between spherical coordinate and the normal coordinate connected by parametric equations. This is an example of coordinates. Dimension and z must be 0. T is parameter, so t minimum is equal to 0, t maximum is equal to times pi, and the calculation is r to equal to t over 6. So we have this polar coordinates, x is equal r times cosine t, and y is equal to r times sine t. We can see here this is 0, and here t is minimum is 0 and t max is 10. So 0, 1, 2, 3, 4, 5 until 10. Follow it, you're gonna see this here, which is the t maximum. This is spherical. P and Q are P minimum is equal to and maximum is equal to times pi. Q minimum is equal to 0 and Q maximum is equal to pi. Calculation R equal to 1.2 P times sine Q. And we got this spherical coordinate. The pair functions on the x and y plane can be expressed by these two planes, x and y. So y is equal to x times cotan p, x itself being function of r, q, and p. The second contour on the y and z plane. So z is equal to y times tan q. This is for the demonstration Okay, so continue.
Yeah, no. We don't have our text here anymore.
In this slide, I want to show you that how to play with the ball, and you're gonna see the how it moves and move it around the X and Y and Y and Z. So to be more clear, 2-dimension and 3-dimension. So we have seen how trigonometric properties influence the behavior of graphs. We have seen how spherical based on trigonometric properties express easily 3-dimensional curvatures. The effect on derivatives on the